Actually, let me give you a little spoiler here. The answer is going to be yes, but still you should find the answer by yourself and prove it. Good. What did we do? We studied two properties of the operator of the equation ax equals b. First one was existence of solutions, and the second, B, was uniqueness of solutions. The first one had to do with, you could spell it out in terms of the image of A being all of Y. The second one could be spelled out in terms of the kernel of A being just 0, or there are these words that many first-year students don't like. I hope you do like them a bit. So this one is surjectivity, and this one is injectivity. And if you have both of them, then that's the perfect situation of bijectivity or invertibility, as we call it. Okay, so A is invertible if and only if we have A and B. Right, now let's come to a situation where A is not invertible. And let me start this with number 2. So A not invertible would mean not both A and B, so it's not A or not B, right? What do you do then? How can you still try to solve the equation? Well, obviously there's no inverse of A, right? So A inverse does not exist. Okay, still try to solve Ax equal B as good as possible. That's the job. Let's do it. So again, did you count? Sets x and y, and there's our operator A. Let me show you the image. Remember, this is a subset over here. And in this case, it's a proper subset, so it's not the whole of y. So it seems that property A, remember, A, existence of solutions, so here surjectivity, or image being the whole of y, is not fulfilled. So the case I'm drawing here is if it's not A, then you will have right hand sides be outside of the image. And that, of course, gives you problems, because whatever little x's over here you try, you always end up in this set. You will never reach B. So what's the best thing you can do? Because we say, okay, then solve it as good as possible. Well, you want to make the error as small as possible. So you say, if I can't get ax minus b down to 0, no matter what x I try, then at least I'd like to make its norm as small as possible. So I'm looking for a x. So now you want this x. So by the choice of x, right? So you minimize this via choosing x. Here you're looking for x such that this expression comes as close as possible to b. So it's of course in y, and moreover it's in the image of a because it's a times something. So which point in the image of a comes closest to b? Well, to me it looks like it's somewhere over here. Let me call this b tilde maybe. Okay, so I'm making this distance as small as possible, and then I get a b tilde which is in the image of a, and I can solve for that one. So I can now find a little x that is mapped onto here. So the length of the green line here is just the expression that you get here, or let me write it differently. You want to lead this to a minimum, and the minimum is just the length of b tilde minus b, because this is now your ax. Okay, so that's the approach for loss of search activity A. So when A is not fulfilled, then that's what you do. Now you can see that also B could be the problem. So what do you do now? So okay, loss of B. What would that mean? Remember, what is B? B is injectivity. Okay, so you might have to solve ax equals b, or as it was in the first case, ax equals b tilde, because you are also losing a. I mean, both could be lost. But trouble is solutions are not unique because you do not have property b injectivity. But you have multiple solutions. Then what you should do is, from all your solutions, so from all x in x with ax equals b, or b tilde if you're in the other case, choose x with a minimal norm. So this time you're not minimizing the norm of the error, you already did that. Now you're minimizing the norm of the solution. Yeah, why not? It turns out that after this two-step process, right? Did you see the two steps? Here is step 1, first minimization process, then step 2. After this two-step minimization process, you get a unique x in x, and that is quite remarkable. So we call that the solution of the least squares problem ax tilde b, because we might not quite reach b, but we do the best we can. Okay, so to see this here in our pictures, we start with the right hand side b. And first of all, we replace b by b tilde, because b might not be in the image. If it is, then b equals b tilde. And then from here, you go backwards to your little x, but trouble is there might be more than one. Okay, there might be more than one little x. And what you do is you're looking for the one that has smallest norm, or in other words, that is closest to 0. So you would then probably pick that one. And that is your preferred x. I said it's unique, and because it's unique, you can now look at, just like we did before, look at the map that brings you from your right hand side b back to your least squares solution x. And unlike in the previous case, we do not denote that map by a inverse, because that notation is already given for something else which doesn't exist in this case. We instead call it the pseudo-inverse, or more concrete, the Moore-Penrose pseudo-inverse, and the notation is A with a little plus sign sitting up here. Okay, so let me just phrase that properly here. So the map that takes your right hand side B into that unique solution X is called the Moore-Penrose pseudo-inverse, shorthand A sub plus. In fact, we will often just say Moore-Penrose inverse. So this Moore-Penrose inverse is doing the job of the inverse as good as you can when the inverse doesn't exist, right? It takes your right hand side and gives you as good as possible solution x in the sense that we mentioned above. Where's this name coming from? Well, it's named after two mathematicians, Eliakim Moore and Roger Penrose. You may have heard of Roger Penrose. Maybe you've seen one of these nice drawings. Roger Penrose is famous for his Penrose tilings. What's a Penrose tiling? He found a way to tile the entire plane by copies of little finite figures. I mean, here you can see them in yellow and white. And the funny thing is that by just copying them again and again in this funny fashion, you can fill the whole plane without the thing being periodic. So so he gave away how to continue this pattern up to infinity, but there is no way you can shift the pattern so it lands on itself. So this point, I mean, you could move it around and try to find another copy of it so the rest again looks the same. You will not. It has symmetries though. I mean, you can kind of see symmetries if you draw lines like here and here and here, here, here. So if you rotate your plane by that angle, which is 1/5 of the full angle, then it will be again the same pattern, but there is no way to translate the plane and it will be the same again. So it's quite an interesting, it's so-called quasi-periodic pattern. Okay.